So this is continuing with modules 9 and 10 in the OLI textbook about the laws of probability. This is in the workbook, modules 8 through 10. It's topic 3 on the logic of events. And so this one's about the law of total probability. You would need to watch the videos on the law of unions and the law of intersections first. Okay, so I'm going to illustrate this with an example. So I've got this repeatable experiment, which is that Magnus Carlsen plays a chess game. So he could do this over and over again. And what we're going to call the outcome, it's the exact sequence of moves for the whole game. The sample space would be the set of all possible outcomes. So that's all the different ways that a chess game could go. Now, these are not all equally likely, of course. You know, he'll try to play a good game. So some sequences are more likely than others. Now, so this box here is representing the sample space, U, the set of all the possible outcomes. And there's really billions of different sequences, different games that could be played. So every little dot here in the rectangle is a possible chess game that could be played, the whole sequence from start to finish. Now, I'm going to define 3 events, B1, B2, and B3. B1 is the event that he wins, and B2 is the event that he draws, and B3 is the event that he loses. And I'm going to draw the event B1 kind of big, because Magnus Carlsen is the world champion. You know, he wins a lot. I'm not saying that the number of games is big. I'm just saying that these ones happen more often. Okay. So this is B1. And then occasionally he'll play a draw. So that's B2. And then B3 is the event that he loses. Now I'm going to define some new vocabulary words here. For one, first B1, B2, and B3, these are all mutually exclusive events. Actually, we did define that before. It means there's zero probability that the outcome, the result of a game, is one where he wins and also he draws. You see, an outcome is going to be either in B1 or in B2, but it's never in both. So the probability of the intersection of any of these two is 0. In fact, there are not any outcomes with chess. There are not any outcomes that are in more than one category. So that's what I mean by mutually exclusive. And then this set of 3 events here is an exhaustive set, meaning that every outcome will be classified as either a win or a loss or a draw. There's not anything left over. So the probability of the union of these 3 events, the probability that one or the other happens, is 1 or 100%. So a set is called exhaustive if the probability of their union is 100%. And these 3 events are mutually exclusive and exhaustive. Now, I'm going to let A be the event that Magnus goes to Disneyland. Okay. Or Disney World. I guess he wants to go to Florida. Okay. So, well, that's the probability that he goes to Disney World. So Some of these outcomes lead to Disney World and others don't. Maybe a lot of the area or the probability is over here and going to Disney World when he wins. But hey, if he draws or loses, he might go anyway, try to console himself. So here's the event A. Now, although this law of total probability has a fancy name, the statement is really simple. That the probability of A is the probability that A happens along with B1 So it's the probability that the outcome belongs to the intersection of these two sets. Plus the probability of A intersect B2 plus the probability of A intersect B3. So there's a certain percentage of the time when he goes to Disney World and he won, a certain percentage of the time he goes to Disney World and he draw, a certain percentage of the time he goes to Disney World and he lost. So you just add those three percentages together. They've got no overlap because of the way B is mutually exclusive. So that's the probability. Well, that's the law of total probability, although you can rewrite it because in the last lecture we learned the general law of intersections. So I can replace the probability of A intersect B1, the probability that A and B1 happen. I can replace that with the probability of A given B1 times the probability of B1 and do that with the other two terms as well. So both of these statements are true. Both of them can be called the law of total probability. In a given word problem, you might have the information you need to use one or the other of these forms, but they both mean the same thing. And so that's about it. Let me just do like an example here. Another example, like let R be the event that it rains. Well, then not R is the event that it doesn't. So you see, whenever you have that kind of situation, like rains and not rains, those two could be your B1 and your B2. They could be two mutually exclusive, exhaustive events. You know, it's on a given day, it's going to either rain or not rain. And so this covers all the possibilities, and it's mutually exclusive. You can't say it did both. And so, you know, so now what's the probability that you go to Disney World? What's the probability You go to Disney World and it rains, plus the probability you go to Disney World and it does not rain. So you'd be able to use this form, or you could change it into these conditional probabilities and solve word problems. You know, maybe the story tells you some of these pieces that you could use in the formula to then work out P of A. Okay, so that's it for the law of total probability. Now, DeMorgans laws they're actually about sets in general. It's not a thing that's specific to probability, but we'll use it. So here I've got these two sets. Well, let's call this set B. And we'll have a set A over here. And I'm just going to make an expression for the complement. No probability, just it's a set of points, okay, or a set of anything. You know, so each individual is a little dot in here. Okay. Now let's do the complement of A union B. So where is that? Now the union, A union B, is the entire inside of the MasterCard symbol, right? It's the whole, it's everything. The union is all of the points that belong to A or B or both. Now the complement of that is everything that's not that. Okay. So let's do that with this green shaded area. The complement of A union B is the outside. Okay. But I want you to notice something. If I take a point out here, it's outside of A, so it's in the complement of A. It's outside of B, so it's in the complement of B. It's in not A, and it's in not B. A point that's not in the union, the complement of the union is the intersection of the two complements. And it's very frustrating that there's more than one notation. Okay. Sometimes you'll see it written this way instead of the not symbol, the little angle bar for not. Sometimes we use an over bar. I don't like that because it looks like the mean. We've been using the sample mean with the over bar, you know, and it's so that I don't use it. But some books would write it this way. Or some of them would write it this way, with a little prime, a little apostrophe for not. Yeah. Or some of them would use a tilde. And that's just really frustrating. In the workbook, I'm going to write it this way. And I forget what your textbook does. I think they're using the little tilde thing. But anyway, it's usually clear from the meaning, but you got to read the words, you know, and see how they set it up. So that's one of DeMorgan's laws. And then the other one is the complement of the intersection. Now the intersection is this little football in the middle. It's what A and B have in common with each other. A intersect B. It's the event that A and B, you know, the outcome belongs to A and it also belongs to B. It's both things. So what's the complement of that? Just everything that's not in the little football. So we're going to shade that up here. Got to be careful to avoid that little football in the middle. That part's left out. So you notice we've included everything that's not in B. You know, if it's not inside the blue circle, it's part of this. The orange part includes everything that's not in the blue. Also includes everything that's not in the red. If you're not in the blue, you're in there. Or if you're not in the red, you're in there. A dot, a point on the diagram belongs. Either it's not in B or it's not in A. So see how that's the complement of A union with the complement of B. And again, if you don't want to use the little angle for your knot, you could use these other notations with the apostrophe or the overbar or the apostrophe or the tilde. So here's one DeMorgan's law, and here's the other one. So what does this have to do with probability? Well, if I want to know what's the probability of not A union B, I can replace the not A union B with not A intersect not B. Depending on the given information in the story, it might be easier to work out this one or that one. The point I'm making is they're equal to each other, so you can use whichever one is easier to find given what's in your story. And so that is all I have to say about DeMorgan's laws.